Thank you very much. It's a privilege to be able to speak today. Today we're going to talk a little bit about radiation dose assessment after accidents. And the main problem with this is you want to assess a person's dose rapidly and typically sort people who have very high doses from those who are with low doses so that you can apply the appropriate medical treatment. We want to look in this particular case at people who do not have radiation dosimetry or are located in areas where the dosimetry limits may be exceeded. We're going to cover today estimated doses from large external sources, estimate radiation dose from criticality accidents, from nuclear weapons, and look at methods to determine a radiation dose after an accident. Sure why. There we go. So immediately after an accident, the main idea is to try to prevent acute effects to people. We want to pull them out of the high radiation areas and move to lower radiation areas. And we want to identify the people who have high doses that will require medical treatment. Usually, radioactive contamination is not as important, except in certain cases. The National Council on Radiation Protection and Measurements recommends that individuals with spot contamination exceeding 37,000 becquerel should be a priority for decontamination. Otherwise, it's not considered a significant problem that would immediately affect the health of people. So how do we determine these large radiation doses immediately? It is very difficult when radiation doses are less than 1 gray. Usually there's no signs of physical impairment and the health of a person is not really impacted at this point, at least not immediately. Long term, there's increased risk for cancer, but typically the only way to determine doses less than 1 gray would be by performing calculations or modeling or using other methods to determine the person's dose. Usually we can do blood samples down to about 0.2 gray, and electron spin resonance has been used down to about 1/2 of a gray. It depends on what materials are present and how the exposure happened. When the dose is between 1 and 2 gray, we can distinguish these people by the time it takes for them to vomit. So at doses between 1 and 2 gray, we'll see vomiting between 3 and 6 hours after the dose. Usually we'll see this stopping within 24 hours. This does not apply to all people, and this is a very general statement. So vomiting isn't always a great indicator, but is one of the very few that we have that is we can easily see, especially in large populations. We can also see a chance of minor bleeding around the gums. We'll see some minor bleeding there occasionally at the higher doses around 2 gray. And we can take blood samples, but this is impractical for large populations in the event of an accident. So once again, we're relying on vomiting to see what happens. As far as 2 to 6 gray, so now we're reaching what's called the lethal dose for 50% of the population. We'll see vomiting between 50 and 100% of the people within 1 to 6 hours after the accident. Generally speaking, the faster a person vomits after an accident, the higher the radiation dose. We start seeing the first cognitive impairment in individuals. And this is greater doses. So as the doses increase, we'll see increased cognitive impairment, and we'll see it happen for longer as the doses increase. Above 2 gray, we expect to see bleeding around the gums, and also on the skin, we'll see reddening of the skin, looks like bruising. Greater than 3 gray, we'll start seeing hair loss, but this doesn't happen immediately. This takes time to occur, but if we're sorting large populations, we might be able to see this in 2 weeks. Again, radiation dose can be determined by blood bioassay, and these people are the ones that can benefit most from medical treatment. The lethal dose without treatment is approximately 3.5 to 4 gray. And these people can be treated, and we want to find them so that we can treat them. The idea behind that is we can rescue these people, and we can sort out those that had lower doses who do not require as much treatment, and those from higher doses where we would just perform more of a palliative treatment. From 6 to 8 gray, we see vomiting less than 2 hours after the dose. As I said before, the faster the onset of vomiting and the greater the population of vomiting with higher radiation doses. These people will have cognitive impairment greater than 24 hours, again, for greater than 24 hours. Impairment possibly immediately. Hair loss may occur rapidly, and we'll see death within 3 to 12 weeks, and these people will seek to do palliative treatment with people who have between 6 and 8 gray. Greater than 8 gray, again, we'll see vomiting almost 100% of the population, generally immediately after receiving the radiation dose. These people will be incapacitated with a large quantity of bleeding, a large quantity of hemorrhaging on the tissues, and we'll expect 1 to 2 weeks before they expire, especially without medical treatment. Again, palliative medical treatment is indicated for these people. So we can determine the dose by the time for vomiting and their cognitive impairment, at least make an estimate. For criticality accidents, we have some other options at our disposal. We can actually measure the sodium-24 activation in the human body. This is an older formula that was produced by the International Atomic Energy Agency, and I believe it would still apply today. The mass in grams of the victim is in the denominator, and then in the numerator we have a measurement of the exposure rate on the person's body. So this would be taken in the person's armpit by placing the detection instrument in the armpit or bending over on the person's body. As an example, I have here a person who is exposed to 0.04 gray of neutrons, would get an indicated activity, and this is in counts per minute rather than becquerel. Immediately following, you can see it's not a lot of counts per minute. So any indication on an instrument after a criticality accident could be a significant radiation exposure. Another method of determining radiation accident exposure is measuring the phosphorus 32 activation in your hair. This is a great way to do it because you can just clip a small hair sample and you can find out the activation of sulfur-32. Again, the International Atomic Energy Agency has a great report on this, and it provides a formula and a preparation method for detecting phosphorus-32 in hair. This is a little more involved than the sodium-24 activation. The sodium-24 activation is very rapid and easy. This is more detailed and might require more time, would not be as useful for large populations. A way to estimate the radiation dose after a criticality accident is something that's called the rule of 7s and 10s. And you can estimate the area radiation dose rate using this rule. If you've taken a measurement and you want to estimate the radiation dose later, every 7-fold increase in time, there is a 10-fold decrease in radiation. Got a brief example. So if we have a measurement at 1 hour, after 7 hours, the radiation levels will be decreased by to 1/10 of the original, and so on as we go through the example. So this is another way we can estimate a radiation dose in a criticality accident. For nuclear weapons doses, there are multiple methods of doing this. You can do the estimate based on distance from the weapon. There are computer programs you can use based on the height of the mushroom cloud. Since this is a pretty specialized area, I'm just going to leave this graph here that shows you the distance for the lethal dose to 50% of the population. We've got, of course, an example here, the dose in gray, the first hour, based on distance and yield of a weapon is given here. And this is just an example so people can see ways of doing this estimate. How about some other methods that we have of determining radiation dose after an accident? These are not so rapid. It's very difficult to determine radiation doses to large populations after an accident through dosimetry methods. But there are biological methods we can use. Unfortunately, these methods take time and they require blood samples. There are facilities that can detect 1/10 of a gray, but there are very few facilities that can do this. Most facilities can detect 0.2 gray or 2/10 of a gray and greater. The higher the radiation dose, the easier it is to detect in the blood, but it is still a time-consuming and complicated process that is not really suitable for large populations. Got a chart here. I'm sorry, it's not in Japanese, but we give the dose in gray and the percent of the people who get that dose who vomit, and the time to vomiting, and then the lymphocyte count as well. And this is a handy chart to give you an idea of what fraction of the population, we know what fraction of the population vomits. We can get a guess as to what the dose is for that part of the population. And then later on, we can do lymphocyte counts on individuals. There haven't been a lot of changes in biodosimetry over the years until recently. We've seen the pseudo-Pelger-Hewitt cell anomaly as an experimental method. Our laboratory is working with Oak Ridge Associated Universities and Fukushima University to look at this as an alternative method of measuring dose through biological samples. When we count lymphocytes, this is a major effort and takes days in order to determine the dose. This particular methodology appears to only require a blood smear and counting of cells in the sample. This is an example that we've found in wild boar that occupy the forbidden, or the region around Fukushima Daiichi. You can see up on the top there is a pseudo-Pelger-Hewitt cell anomaly, and on the bottom we have stained a normal cell. This procedure appears to work in humans, wild boar, but not in mice. The pseudo-Pelger-Hewitt anomaly is not expressed in mice. We're still uncertain if there is a linear response over all conditions, and we're currently doing some research to determine linearity of response as well as long-term irradiation and other aspects of this anomaly. So this is an up-and-coming, possibly, method that we could use to measure radiation dose rapidly. For radiation doses from inhalation of radioactive material, one of the easiest things to do in a large accident is to take nasal swabs and count them. They do not always represent the intake of radioactive materials, but they do give us an indication that something has occurred. So we can't really estimate dose from a nasal swab, but we can tell if a person has inhaled something. As far as bioassay is concerned, in my terminology here, there are two methods of bioassay. One is where we take a radiation detection instrument and we measure the photons emitted from the body, from the deposited radioactive. We call this in vivo analysis. In vivo analysis is useful for high energy gamma emitters, some lower energy gamma emitters, and if we have large deposits of beta emitters, we can detect the bremsstrahlung radiation. For in vitro analysis of radioactive material, that requires urine or fecal analysis. The in vivo analysis can be done possibly with large populations in an accident, but again, it's not really suited for quantitative analysis of large populations, but qualitative analysis could be accomplished. For in vitro analysis, this is again a long and more individual process that is not suited for large accidents, but more for individuals and accidents. Electron spin resonance is a useful methodology for external gamma ray exposure only, and generally only for above 1/2 gray. Unfortunately, it also requires some time and is not really suitable for large populations, but we could do estimates after the accident and take samples of materials in the vicinity of the accident and use that to estimate the radiation dose. Mathematical estimates of radiation dose, especially for photon measurements, is much easier and not as time consuming. If we take measurements at different distances, I think most folks are familiar with this. We call it the inverse square law in my world here. And I just have a brief accident. If we take one measurement, we can estimate the other measurement just through a simple calculation. And these calculations, although they appear simple, frequently are quite good and give us a great estimate, and it's, of course, very rapid. So in summary, we've also got some software that I can recommend as far as bioassay. The biodosimetry assessment tool and WinFRAT, these are both available from the Armed Forces Radiobiology Research Institute in Maryland. I've got a link here in case people are interested, and you can download the software for free. And with that, I'll conclude my talk. If you have any questions, please let me know. I'm happy to help out in any way I can.